So there are a number of aspects of a periodic motion, and in this session we will begin with the case of simple harmonic motion, which is the simplest form of the periodic motion. So we can define simple harmonic motion as a motion in which the acceleration of the body is directly proportional to its displacement from a fixed point or a mean position, and it's always directed towards a fixed point. So simple harmonic motion is basically a motion in which the acceleration of the body is directly proportional to its displacement. Now this simple harmonic motion possesses some characteristics such as the motion is always periodic. Then when displaced from the fixed point, right, when the particle is displaced from the fixed point or the mean position, the restoring force acts on the particle, tending to bring it to its mean position again, right? So whenever any particle which is performing simple harmonic motion, there will be a restoring force acting on the body that will try to bring the body to its mean position or the equilibrium position again. Okay, so third characteristic is the restoring force on the particle is directly proportional to the displacement. So these three are the main characteristics of a simple harmonic motion. The first one is that motion is always periodic. Then when the particle is performing simple harmonic motion, right, from the fixed point or mean position, restoring force will act in such a way that it will try to bring the body or the particle to its original position again, right? Then restoring force acting on the particle is always directly proportional to the displacement of the body or the particle, right? So these three are the main characteristics or feature of a simple harmonic motion. So it should be noted that the study of simple harmonic motion is of practical interest, right? For example, a vast variety of deformation of physical systems, like for example compression, bending, stretching or twisting or combination of all this, right, involves restoring force that is directly proportional to the displacement and hence leads to simple harmonic motion. So now let us see an example of simple harmonic motion. So as you can see in this diagram, let us consider a particle A which is moving along the circumference of the circle, right? Let O be the center of the circle, right? So let us consider that particle A is moving along the circumference of the circle with constant speed v, which is equal to r omega, where r is the radius of the circle and omega is the angular speed, right? Now let AP perpendicular be drawn from the center of the circle, and the perpendicular AP be drawn from the particle on the diameter yy dash of the circle, as you can see from this diagram, right? Now as the particle moves along the circumference of the circle, the point P, the foot of the perpendicular, vibrates along the diameter. Since the motion of A is uniform, the motion of P will be periodic. Now the distance OP from O will be the displacement, and let us say the particle moves from x to A in time t, then we can say that AOX is equal to PAO is equal to omega t is equal to theta. So as the particle moves along the circumference of the circle, the point P, the foot of the perpendicular, vibrates along the diameter, right? Since the motion of A is uniform, the motion of P is periodic. Okay, so distance OP from the center of the circle will be the displacement, right? And if we say the particle is moving from x to A, point A, in time t, then we can say that AOX is equal to PAO is equal to omega t, which is equal to theta. right? So from the diagram we can also say that OP is equal to Y is equal to R sin omega t, right, which indicates, which expresses the displacement of the body moving along the circumference of the circle. So we know that velocity is nothing but displacement, the variation of displacement with respect to time, right? Or displacement with respect to time simply, or distance with respect to time. So here we know that displacement is expressed in terms of y. It is noted by y. So y is equal to r sin omega t, right, represents the displacement of the body. So velocity will be change in displacement with respect to time. So it will be dy by dt, right? So we have to differentiate this y with respect to t. So we know that the differentiation of sin omega t is cos omega t, right? And also omega will appear ahead of this equation, and also omega will be there, right? So the velocity v is equal to r omega cos omega t. Okay, now let us equate this expression. For example, r omega cos omega t, in this term cos omega t can be written in terms of sin omega t, right? We know that cos square omega t plus sin square omega t will be 1. So cos omega t can be written as 1 minus sin square omega t raised to 1/2, or root of 1 minus sin square omega t, right? So now velocity is r omega 1 minus sin square omega t raised to 1/2, right? Now from this equation, the displacement equation, y is equal to r sin omega t. So from this equation we can say that sin omega t can be written as y by r, right? So substituting this in equation 1.1, right, we'll get v is equal to 1 minus y square upon r square raised to 1/2. So the velocity, the equation of velocity will be 1 minus y square by r square into raised to half into r omega, right? Since sin omega t is equal to y by r, so substituting this equation will get the velocity equation, which is 1 minus y square by r square raised to half into r omega. Now if we want to derive the equation for acceleration, then we know that acceleration is d square y by dt square, or we can say that dv by dt. Acceleration is change in velocity with respect to time, right? So either we can double differentiate the equation of displacement, or we can simply differentiate the equation of velocity, right? If we differentiate this velocity equation, which is v is equal to r omega cos omega t, so we will get minus r omega square sin omega t, since the differentiation of cos omega t will be minus omega sin omega t, right? So minus r omega square sin omega t will be the equation of acceleration. Now r sin omega t represents the displacement of the particle. So if we substitute y instead of r sin omega t, so we will get acceleration in terms of displacement as minus omega square y, right? So these are the equation of displacement, velocity and acceleration in terms of in case of simple harmonic motion. Okay, so if we want to find the velocity, we can get it from differentiating the displacement equation. So displacement is given by y is equal to r sin omega t, right? So if we differentiate this equation, we'll get r omega cos omega t. Now cos omega t can be written as 1 minus sin square omega t raised to half, or root of 1 minus sin square omega t, right? Again sin omega t can be written as y by r. So substituting this value, will get the velocity equation as r omega 1 minus y square by r square raised to half, right? This is the velocity equation in terms of displacement. Now if you want to find the acceleration, acceleration can be obtained from differentiating the velocity term, right? V is equal to r omega cos omega t. Now the differentiation of cos omega t will be minus omega sin omega t. Okay, so we'll get acceleration as minus r omega square sine omega t. Now again r sine omega t is the displacement, right? So acceleration can be represented in terms of displacement as minus omega square y. Okay, so now let us see time period. What does time period means? So the time required to complete one complete oscillation is known as time period, right? The time required to complete one oscillation is known as time period. So it is expressed as 2 pi by omega, right? Or we can say omega is equal to 2 pi by t. Right, now omega is the angular velocity. Angular velocity is defined as the ratio of angle described in one revolution to time taken for one revolution. Okay, the ratio of angle described in one revolution to time taken for one revolution defines angular velocity. It is mathematically expressed as omega is equal to 2 pi by t. So T is the time period, capital T is the time period, time taken to complete one oscillation, and omega is the angular velocity, which is the ratio of angle described in one revolution to the time taken for one revolution. So if we substitute the value of omega from equation 1.2, that is equation of acceleration, right? So here acceleration is equal to minus omega square y, or if we neglect the sign, then acceleration is given by omega square by y. So omega square will be acceleration upon displacement. Y is the displacement. Then omega is equal to root of acceleration upon displacement. So if we substitute this value into this equation of time period, we'll get time period as 2 pi upon root of acceleration upon displacement. Now this acceleration upon displacement can also be written in terms of acceleration per unit displacement, right? So T can be written as 2 pi root displacement upon acceleration. Remember that frequency n is simply inverse of time period, right? Frequency is simply inverse of time period. So frequency is denoted by n here, sometimes it is denoted by f also, right? It is inverse 1 upon t. Okay, so now let us see some energy types of wave motion. Then we'll start with potential energy. So we know that potential energy is force into distance. Okay, now work done in moving through dy displacement is given by m omega square y dy. If we integrate this with respect to y, right, we'll get m omega square. Right, if we differentiate this equation with respect to y, the integration of y will be y square by 2. So we'll get m omega square y square by 2. Again, what is y? Y is the displacement, which is represented as r sine omega t. So if we substitute this value, we'll get m omega square r square sine square omega t upon 2. So this expression is the expression for potential energy in case of simple harmonic motion. Now let us find kinetic energy. Kinetic energy, we know that is v square upon 2. What is v? V is the velocity, right? Kinetic energy is always expressed as half mv square, where v is the velocity of the particle, right? So v is expressed as r omega cos omega t. So let us substitute the value of velocity of the particle here in case of simple harmonic motion, which is r omega cos omega t. So we'll get kinetic energy as m omega square r square cos square omega t upon 2. Right? We know that total energy is the sum of potential energy and kinetic energy. So substituting the value of potential energy and kinetic energy, which is derived here as m r square omega square by 2 sine square omega t plus m omega square r square cos square omega t by 2. So we can see clearly in the equation of potential energy and kinetic energy that m omega r by 2 are common. Right, so taking common in both this equation, m r square omega square by 2 will get cos square omega t plus sin square omega t left out, and we know that the sum of cos square omega t plus sin square omega t is nothing but 1. So we're left with m r square omega square by 2. Right, now r omega, right, r omega is the angular speed. Okay, so the angular speed is denoted by capital V. So r omega can be written as capital V, right? So we'll get the final total energy as mv square by 2. So this is all about simple harmonic motion. Thank you.